So similar triangles are a very important topic because they crop up a lot in mathematics and in real-world problem solving. And there's a variety of ways that you'll be presented with similar triangles. One way is what I've shown here, where you have essentially a triangle inside a bigger triangle. So in order to know that triangles are similar, you have to know that the interior angles are the same. That's actually sufficient with similar triangles, to know that they are similar, because there's really only one sort of shape of triangle that you can construct with any three angles. And since we know that the sum of the angles, interior angles of a triangle, is 180 degrees, if we know two of the angles, then we can figure out the third very easily. So in practice, all you actually need to know are that two angles are corresponding or the same in triangles to know that they're similar. So I've actually given you more information in this triangle than you might otherwise get. I've indicated all of the angles, and you can see that we have angle A is 50 degrees, and that's the same as angle D. We have angle B is 100 degrees, and that's the same as angle E. And then angle C is actually shared by both triangles, and it's obviously 30 degrees for both triangles. I've also indicated that AB is parallel to DE, and that is symbolized with the small arrows on the line segments. So if that was all we knew, if we knew that those line segments were parallel, then we would know that angle A and D were the same. We wouldn't actually have to know what they were in order to be able to determine that these triangles were similar. That would be sufficient. So let's take a look at some problems that we can solve or that you might be faced with. I've labeled some of the segments of this diagram. So the line segment CD is labeled with 15 and DE is with 7. So that's pretty good because we have two sides of that triangle labeled. And then I have AB labeled with 14, and that's a side of the larger triangle. And here's where you have to be really careful. BE is labeled with 12, and the temptation is when you set up the ratios to solve something that you're looking for in this triangle, you'll use BE, but you have to be really careful because BE is actually not part of a triangle. It is part of the length of BC, which is one of the lengths on the larger triangle, but BE is not itself a length of a triangle. So we'll have to deal with that a little bit more carefully. Let's do an easier problem to start with. Let's say we want to find AD. Now, again, AD is not part of a triangle. So what we have to do is we have to say, well, we know what the side length DC is along that smaller triangle. So we can find AC. So let's find AC first. So AC is the length along the bottom across from the angle 100 degrees of the larger triangle. So the corresponding side on the smaller triangle has a length of 15. And so since we started with the larger triangle on the left, we've got to start with the larger triangle on the right, and we have a pair of corresponding sides. 14 is the side opposite the 30-degree angle, and so is 7 for the smaller triangle. And now we've got everything we need to solve for AC. So we can multiply both sides by 15 here. And on the left, we get AC. On the right, 14 over 7 is just 2, and 2 times 15 is 30. And I've chosen pretty easy numbers for this because, it's pretty obvious that the larger triangle, all the corresponding sides are just double the smaller. So I wanted to make it kind of obvious here, but it is definitely not going to be necessarily so easy on some of the problems that you're going to look at. So remember, AC is not actually what we were looking for. We were looking for AD. So what is AD? AD is AC minus DC, and AC has a length of 30 and DC has a length of 15. So AD is actually a length of 15, and we can write that in. So we can do something similar to find CE. And here's where we've got to be really careful, because CE is definitely part of a triangle. It's part of the smaller triangle. So when you're setting these ratios up, I always suggest starting with whatever you're looking for as the numerator. If you start with a side that's known and you put the unknown in the denominator, you'll end up with a ratio that's just a little trickier to deal with. So in this case, we don't really have a choice though, because we're going to start with CE, what we're looking for. the corresponding side is, again, the side opposite the 50-degree angle. And in the bigger triangle, we only know part of that. We know 12, but the other part is actually CE itself. So we end up with CE plus 12 for the denominator. Now, on the right-hand side, things are a little better, thankfully. We have started with CE, which is from the smaller triangle, so we need to start with the smaller triangle, and we have a side 7 that we know. And that's the side opposite 30. The corresponding side opposite 30 in the bigger triangle has a length of 14. So we can work with this, but it is a little bit more work. Let's first simplify the 7 over 14 and write that as a half. So we have CE over CE plus 12 equal to 1 over 2. We can now multiply both sides by both denominators. And, when you have a fraction equal to a fraction, the result is something that students like to refer to as cross-multiplying. So we end up with 2 times CE on the left and 1 times CE plus 12 on the right. So we have 2 of our unknown on the left, 1 of our unknown on the right. We can subtract CE from both sides and end up with just 1 CE on the left and 12 on the right. And that is exactly what we would expect it to be. So CE is 12, which then makes that entire length going all the way from C to B, 12 plus 12, or 24, twice the length, which is what we expected. Now, there are actually some very interesting practical problems that you can solve using similar triangles. One is to find the height of objects. So let's say you have a tree and you want to find the height of that tree. Now, you need to have a few things working in your favor. It has to be a sunny day, and the tree has to be casting a shadow on a level ground. And then you have to have a long enough measuring tape to be able to measure the length of the shadow. So we're looking for the height of the tree, and let's say the length of the shadow is 36 meters. Now, what you do then is take something small that you can measure the length of and make sure it's perpendicular to the ground and try to measure the length of the shadow of that small object. And the easiest thing to work with is something like a meter stick. So a meter stick has a height of a meter, so just 1 meter there, and you measure the length of that shadow, and let's assume it's 1.2 meters. Now, are these actually similar triangles? Well, you want to be able to hold the meter stick perpendicular to the ground, and you sort of assume that the tree is growing perpendicular to the ground. The length of the shadow of the meter stick can obviously be measured quite easily. The length of the shadow of the tree is a little trickier because we actually kind of want to go to the center of the tree. So you might have to actually add a little bit to the length of your shadow of the tree to make sure that you're getting a point directly underneath the tip of the tree. The other thing is, are these really similar triangles in terms of the angles? Well, we've got 2 perpendicular angles, but what about the angle between the sort of this angle here formed by the light rays from the sun? So as long as we measure these shadows at the same point in time, the sun will be at the same angle to the horizon, and therefore those angles will be effectively the same. If we were at some very different point on Earth doing this, then obviously the angle wouldn't be the same. But for practical purposes, you'd have to be a long way apart in order for the angles to be any different. The time definitely matters, though. If you measured the angle of the sun at 5 o'clock and then came back again and measured it at 6, it's going to be quite different. So as long as you're measuring these shadows at roughly the same time and in reasonably close proximity, they are indeed similar triangles. So let's see if we can set up the ratio. We're looking for the height and the height of the tree, and that corresponds to the height of the meter stick, which is a convenient value of 1. And then we get the length of the shadow of the tree, which is 36, and that corresponds to the length of the shadow of the meter stick, which is 1.2. H over 1 is obviously just h. 36 over 1.2 is 30. So the height of this tree is 30 meters. And, that's quite quite nice. We didn't have to do anything terribly sophisticated. We didn't need trigonometry or any way to actually measure the angle. We just needed to measure angles along, or measure shadows along the ground. Let's see if we can do something even trickier. What if we are standing at a riverbank and we'd like to know the distance across the riverbank? So let's say there's some kind of landmark, some stone or tree or something on the far side of the riverbank. And we get ourselves to the other side of the river. And we're going to have to go a little bit beyond the edge of the water to some sort of level ground. So again, we're going to need to have a fortuitous place to do this. And then we're going to need to walk ourselves down the riverbank at a perpendicular to the sort of sighting across the river. And if you have, certainly draftspeople, if you have any kind of rudimentary tools, it wouldn't be too hard to actually get this kind of right angle going. And then we can imagine a line going to our new point and then extending beyond, and then we can extend our walk along the riverbank a little bit as well. So here we have two triangles, and as long as we make our little additional triangle on the riverbank a right triangle, these are guaranteed to be similar triangles. Why? Because you've set it up so that you have these opposite angles here, and opposite angles are equal. So we don't need to know what those angles are, and we don't need to walk down the riverbank any particular distance. We just have to be able to measure it. So these are similar triangles, and let's say the length of this leg is 5 and the length of this leg is 20. Now we're looking for this distance, and then all we need to do is measure this distance here, 7. And you can pretty much see what's going on here. The small triangle has been multiplied by 4 to get the big triangle, and so you know pretty much right now, without even setting up the ratios, how long d is. But let's go ahead and do it formally. So if we're looking for d, let's put it in the numerator. D corresponds to 7. They're both opposite those angles that I've labeled with a dot. And then we have these lengths 20 and 5, which are corresponding. And so now I can multiply both sides of this by 7, and I get d on the left. 20 over 5 is just 4. 4 times 7 is 28. So the length across this riverbank, or at least from the point on the riverbank where we constructed the right triangle across to the whatever the rock or the tree or some landmark on the other side, that distance is 28 meters. And so again, this is pretty interesting because we might not have any physical way of actually getting across the river, but yet we can still measure it using some fairly basic tools.